Lesson number 6, laws of logs. All right, here we go. Just like we had laws of exponents, we have laws of logs. I'll just get rid of this. Okay. Now, multiplication law, so similar to laws of exponents, but opposite of what you would think. Because laws of exponents, when you're multiplying with the same base, we add our exponents. Now with logs, if we're adding with the same base, we can multiply these terms and combine the logs into a single log. So adding with the same base, we have a product. And these laws can be reversed. If we started with a product, we can break the log up into two separate logs using addition. So when we have subtraction, we do the opposite of multiplying, we divide. So when you're subtracting, as long as the bases are the same, then we write it as a single log using division. This is a really common one, and this is when you have a term with an exponent. The x has an exponent. That exponent can be moved to the front of the log. So this is going to work both ways as well. When you have a number or a coefficient in front of the log, that can be moved up to the exponent position. So back and forth that way. Now if we have a radical, so lots of times you see radicals in this position, we could change that radical to an exponent that's a fraction, and then that can be moved into the coefficient position or in front of the log. So the last rule here is the change of base rule, which we've talked about a few times. I think most people are understanding now that the base is the denominator when we type it into our calculators. So we ignore the base for the numerator, log x, divide it by log b. We can change any base to base 10. So we use base 10 because our calculators are base 10, but we could change any base using this rule. Okay, so the natural log base e, we don't use that in this course, so I'm just going to ignore that. So evaluation of each of these logs. Before we evaluate, let's put, well, the first two examples, let's put them into a single log. If I try to evaluate this as it is, 5 to the power of something is 100, that doesn't work out nicely, so I couldn't do that without going to my calculator and getting a fraction or decimal answer. But if we combine these into a single log, this could be evaluated easier. So I'm going to combine it because they're addition of two logs with the same base. I can multiply the 100 and the 1/4. And this gives me log base 5 of 25. Log base 5 of 25, we know this equals 2. 5 to the 2 is 25. So now that can be evaluated. Okay, let's do another one. Now this is adding and this is subtracting. So we can combine this in one step. Log base 6, 9 times 8 over 2. 9 times 8 over 2 is log base 6. 72 over 2 is 36. 6 to the power of something is 36. That is equal to 2. So evaluating them separately, not easy. But doing a combined, putting them into a single log, makes it very easy to evaluate. All right, we have radicals going on here. So that's okay, let's put them together. We have subtraction, so log base 3. So remember when we're dividing with radicals, if we can divide the radicands, if they divide evenly, we can go ahead and divide them. And root 45 over root 5 divides nicely into root 9. Well, I can handle this a couple of different ways. I could change this to log base 3 of 3 because square root of 9 is 3, and that equals 1. I could change this to log base 3 of 9 to the power of 1/2, and then move the 1/2 into the front of the log, using the third law of logs. I think I'll just leave it the way it is right now, because we are going to use that law of logs in another example. All right, I'm going to switch colors here so you can see the separation here. Log base 3 of let's see, log base 3 of 5th root of 27. I don't know what the 5th root, if that was cube root, I would go ahead and cube root 27, but it's the 5th root, and that's not a nice number. I don't know what the 5th root of 27 is, so I'm going to write it like this. I'm going to change the root to an exponent 1/5. Now that exponent, if you remember the third law of logs, can be moved to the front of the log. So this becomes much easier to evaluate, because 3 to the power of 3 is 27. This log is equal to 3. So by moving the exponent 1/5 to the front, I could then evaluate the log and then multiply it by 1/5. Now let's look at this E example. We have brackets, so let's evaluate inside the bracket first. This 2, I can't combine logs with adding and subtracting using my first two laws. If I have a coefficient in front, that has to be dealt with first. So that is going to go up here, and this is going to become log 18 divided by, because I have subtraction, 3 squared. So the 2 got moved up there first. So 3 squared is 9. So now I have this, log 18 over 9. I have no subscript. This is base 10. So I'm going to do this, log base 2. Sorry, it's log base 10. Now I'm subtracting, so it's 2 over 2. Log base 10 of 1. 10 to the power of what equals 1? 10 to the power of 0. So I had all three, actually 2 laws of logs going on in this example. I had moved the 2 up to the exponent position, then combined, because it was subtraction, I combined using division, and then I did it again because I had subtraction again. Let's try another example. All right, write as a single log and state restrictions. So we have to be careful with restrictions here. So if I use this as an example, y equals log base 2 of x. A reminder here of our domain. With our log functions, our domain here is x is greater than 0. Remember that vertical asymptote. That vertical asymptote means we have restrictions on our domain. So look at the position that x is this term, this term, this term. These are all in the position that x is in. So our restriction here, this is base 10, is this. And if we, why did I put a 2? Oh, let's see. There's 2 different restrictions. We have a minus 1 and a plus 2 have to be greater than 0. So let's isolate for a. Remember when we have 2 restrictions for a single problem? It's the overlap. What is the overlap between these 2? Sometimes we have to look at it on a number line to get a good idea. So the overlap, if we think of greater than negative 2, not equal to, so empty circle, would look like this. And greater than 1 would look like this. So the overlapping part is this one. So if you're ever not sure, draw it on a number line, and that will give you your answer. But then we have to simplify this. It says write as a single log. So putting this together as a single log, I'm going to change colors here. Log, because it's addition, I'm going to multiply. A a plus 2 and a minus 1. Plus 2a minus 1a is plus a minus 2. So as a single log, it would look like this. The base is 10. Really, a bracket around that term would be required because we have 3 parts to that term. It's a trinomial. We should have it in brackets. But the base in that example is 10. I don't have to write it in. Now let's look at the restriction in this example. I have a, 2b, and 5th root of c. None of these can be negative, so they're all greater than 0, and they're all different. So I would just write a is greater than 0. That's it. That's the restriction. Now, running out of space here to combine these, I would do subtraction here. I have a coefficient that needs to get moved. So that coefficient, be careful because 2b is raised to the power of 3, not just b. Now this 5, I'm going to move up here, and I hope you realize now that root 5 of c raised to the power of 5, that's just going to equal c. So putting this together, log, this is subtraction, so it's going to be a over 2b cubed. Now we have addition, so this is going to get multiplied by c. So multiplying that fraction by c is just going to put it in the numerator. Again, we have base 10. I don't need to write a subscript. But I can cube the denominator. This would be 8b cubed. I should put this in brackets. I'm going to rewrite this a little neater. And that would be as a single log with these restrictions. All right, these next two look pretty complicated. Let's work through these. Again, we're looking at writing as a single log. We have brackets, and that 1/2 is in front of the bracket. So I'm not going to change this. I'm going to leave this for now and put these 2 logs together. This 5 goes here. It's addition, so I can write this as log base 3 x times x to the 5. X times x to the 5. So in the next step, maybe I'll move the 4 up to here. So log base 3 x to the 4 minus, now this x to the 5 times x is going to become x to the 6th. Log base 3 x to the 6th. Now this 1/2 that was in front of the bracket, I'm going to move it up to the exponent right here. And let's see if I can make a little bit more room for us here. This was an added-in example. That's probably not in your notes, but it's a really good example, so I really want to keep that. So let's keep going with this one. Log base 3 x to the 4 minus, if I multiply those exponents, I have log base 3 x to the 3. Now I'm subtracting, so I'm going to combine it into a single log. X to the 4 over x to the 3. And that equals log base 3 of x. Single log. Was there any restrictions in this example? Let's go look at the original. So we had x, we had x, we had x. So only restriction here is that x is greater than 0. So our domain is greater than 0. Okay, let's go to D here. I don't have any coefficients in front. So we can go ahead and combine these into a single log using division because we have subtraction between the logs. So I'm going to write this as log base 2 Now this time we definitely have restrictions. This can't equal 0. So before we do restrictions, let's take a look at simplifying this. So we also can't have this being undefined. If we have a fraction here with variable in the denominator, we have x can't be 3 and negative 2. But we also have this entire fraction has to be greater than 0. So we know it's going to simplify because we can reduce. So this is going to reduce to log base 2. And that would be the final single log. But going back up here, at the original term here, we had x squared minus 9. This whole thing has to be greater than 0. So if we go to simplify this, what that means, if we multiply by the denominator just cancels because 0 times the denominator is still 0. So that leaves us with this. X squared minus 9 is greater than 0. So if we think of that on a number line, on a graph, x squared minus 9 is something like this. We have a 3 and a negative 3. That would be x squared minus 9. Give us a little more space again. So where is this possible? We need this to be greater than 0. So it's greater than 0 on this side and this side. So there's two parts where this will work. And the two parts are greater than, not equal to, 3, and less than negative 3. And it can't equal negative 2, but negative 2 is not less than negative 3. Negative 2 is in this section. So we don't have to worry about that restriction. It's already taken care of. X can't equal 3 is already taken care of because it has to be greater than 3. So just stating these two, that's it for your restriction here. So that's a little bit more complicated for a restriction, but that is not unusual when you have a quadratic in that x term. All right, let's continue here with this challenge question. I'll get rid of this again. There we go. All right, this is an interesting question. We've seen this come up on diplomas before, so we want to make sure you can express as a single log if one of your terms is a constant. Sounds weird because we don't even have two logs. How can we combine them? But what I want you guys to understand is that you can convert any constant into a log. So I can write this as log base 3 because I want it to match this log base 3 in order to convert them or to combine them. Now, what should I put in here to make it equivalent to 2? I want this log to equal 2. So if I put a 9 here, 3 to the power of 2 is 9, these are equivalent expressions. I'm just changing a constant into base 3. Now that I've done that, I can't quite combine them yet because the 7 has to be removed. Log base 3 of 9. And I'm going to write the 7 as the exponent. Now I'm ready to combine them using multiplication. So that's going to be 9 times x to the 7, or just 9x to the 7. That would be my single log, which is equivalent to the initial expression. So using a log to represent a constant. If I wanted to write, let's say 4 as a log of base 2, what would I put in for the x term? I'd put in 2 to the power of 4 because this expression is equal to 4. Log base 2 of 16 is equal to 4. So I can replace any constant with any base. All right, these questions really common with the laws of logs lesson here. We want to represent log base 4 of 45 in terms of x and y. So I know that x is using is equivalent to log base 4 of 5. Y is equivalent to log base 4 of 3. So if I can break this up, log base 4 of 45, where it equals a value of x and y, and you know that 45 has factors of 5 and 9. So let's break it up into log base 4 of 5. We know that's equal to x, plus log base 4 of 9. So y is equal to log base 4 of 3. And I can continue breaking up log base 4 of 9 into 3 squared. Log base 4 of 5 plus log base 4. I'm going to move this down slightly to give us a little more space. So I know this is equal to x. This is almost equal to y, except there is an exponent of 2 here, which I can bring out to the front and write this as log base 4 of 5 plus 2 log base 4 of 3. Now I know that this expression is equivalent to x plus 2y. Kind of neat how we separated that into x and y. All right, now you try 81 and pause and then go through my work. So log base 4 of 81. I know 81 does not have a factor of 5, but 81 is a power of 3. Just like we use 9 as a power of 3, I know 81 is a power of 3. I'm going to write this as log base 4 of 3 to the 4. So 3 to the 4 means that the exponent 4 can be moved out to the front of the log. Now I know log base 4 of 3 is equivalent to y, which means this is equivalent to 4y. What about 225? What are the factors that we can break 225 up into? 225 goes into 25 9 times. So we have a power of 3 and a power of 5. Let's do that and break log base 4 up into log base 4 of 25, log base 4 of 9. 225 is equal to 25 times 9. So we can break it up. So you see just from the last examples what we're going to do here. This is going to be 5 squared. This is going to be 3 squared. The 2 is going to move in front of the log. Let me move this out of the way. Now we have our values of x and our values of y. So we can write this as 2x plus 2y. Well, this looks a little more interesting. Base 2. Let's save that base 2 till the end here. What about 100? 100 is not a power of 5. It's not a power of 3. Does it have factors that are powers of 5 or 3? Well, 25 is the only power of 5 that is a factor of 100. So I can break this up using my law of logs into 25 times 4. So this is still going to work because we can change 25 into 5 squared. And log base 4 of 4, make that a little neater. Anytime these numbers match, this is always equal to 1. 4 to the power of what is 4? Any number that where this term is equivalent to the base, that log is equivalent to 1. So we can evaluate that because it's base 4. Now we can change the expression on this side. Here is our value of x, so that's going to be 2 log base 4 of 5. So this is the same as 2x plus 1. All right, let's look at that last one. I'm going to move this down because I think we're going to need a little bit of space for this one. Log base 2 of 15. Okay, the problem is that we have log base 4 of 3 and log base 4 of 5. So this is what our x value equals. This is what our y value equals. They're both base 4. We cannot break up base 2 and make this work. Let's change the base. So let's go to exponential. 4 to the y is equal to 3. Well, if I want to change my base to 2, I'm going to say 4 is 2 squared. So if I change the base to 2, then I have to multiply my exponents. This is what base 2 would look like. So what would this look like as a log? Log base 2 of 3 equals 2y. We could do the same thing with our x term. We could say 4 to the x equals 5. Change it to base 2. Change 4 to 2. That means we have an exponent of 2 times x is 2x. And that, if we write it as a log, is now base 2. So this expression in base 2 is equivalent to 2x. This expression is equivalent to 2y. Now we can break up the log base 2 of 15. Whoops, I don't want to do that. Log base 2 of 15 is equivalent to log base 2 of 3, because 15 is 3 times 5. Now we can replace this with 2y, this with 2x, and there we go. We have now expressed it in terms of x and y. There's some great homework questions that involve very similar problems. All right, let's look at pH. pH is really common with logs. It's one of the few formulas that actually uses a log. So here's the formula. pH equals minus log base 10 of H plus. Sometimes you don't see the 10 written in. Either way, it's base 10. Now if we rearrange this, it makes these questions a lot easier. Sometimes you're given the pH, sometimes you're given the hydrogen concentration. This is the acidity. This hydrogen concentration is referred to as the acidity of a substance. So if we rearrange this formula in terms of pH, so what I want you to see is that the base is 10, and, oh, 1 second here. I want to get rid of the negative first, so negative pH is equal to log base 10 of the H plus. All I did was get rid of the negative first. Now I'm going to switch to exponential. 10 to the power of the negative pH is equal to the hydrogen concentration. So this is the formula we're going to use to answer the next couple of questions. All right, a cola drink has a pH of 2.5. Milk has a pH of 6.6. How many times more acidic is cola than milk? So a cola drink has pH 2.5. So that means the pH is going to go to the exponent, and that's going to be a negative 2.5 as the exponent to base 10. Now milk is pH of 6.6, so that's going to be the exponent of negative 6.6. And if we're looking for how many times more acidic, that means we're dividing the hydrogen concentration of cola by the hydrogen concentration of milk. And just remembering that the exponents are negative because the pH is a negative when we rearrange the formula to isolate for H. When we subtract our exponents, we get 4.1, but it's 10 to the 4.1, which is 12,589. That's how many times more acidic that a Coke drink is than milk. All right, now we're given apple is 5 times as acidic as a pear. So that means that the fraction that we just worked with right here is equal to 5. If a pear has a pH of 3.8, so we said that the hydrogen concentration of a pear over the hydrogen concentration of an apple, or an apple is 5 times more acidic. If the apple is 5 times more acidic, that means that the apple over the pear is equal to 5. Now, the pear has a pH of 3.8. So that means in the form that we were looking at up here, isolating the hydrogen concentration, we would put the pH in the exponent, so that's negative 3.8. And this is going to be the pH of the apple. So in order to isolate the pH of the apple, we're going to multiply 5 times the 10 to the negative 3.8. That's going to give us the hydrogen concentration of the apple. And then it says, what is the pH of the apple? Well, when we times these two numbers, we get this. What we're going to do is 5 times 10 to the negative 3.8. We actually can put it right into our original formula. Once we have the hydrogen concentration, we can do this and put in 5 times 10 to the negative 3.8, and that will give us our pH. So we're going back to the original log formula to calculate the pH, which works out to 3.1. There is a really good example of pH questions in the assignment as well. All right, that's the end of lesson 6. Now let's work hard on these assignments, get them complete, and last lesson tomorrow.